Yeah, thank you very much for introduction. Just before this discussion, the many scholarships students are coming to the nuclear engineering, and actually, I'm working on the nuclear engineering for more than 40 years as a professor at the University of Tokyo. The University of Tokyo is one of the biggest universities in Japan, and having lots of the experiences on the nuclear safety and something like that. And in my laboratory, I have many foreign students, including Poland, Turkey, India, or something. So if you are welcome to coming to Japan, and it is a little bit far away, but I believe that our student experiences are very good for young students. Actually, the 20 years ago, one of my students from China is now coming back to the China to be a professor or another important person to constructing the safety nuclear reactors in China. So that I believe this kind of the practice will be good for, especially for the students coming to the not only Japan, but another country is good. But I'm as I talking, I'm belonging to the nuclear engineering management department. So please think about the sending us the good students, and I would like to have a good communication with Japan and Estonia. Okay, now I'd like to a little bit talk about the nuclear safety. Actually, as you know, we have a Fukushima Daiichi nuclear power plant accident almost 30 years ago. And from lessons learned from this kind of the accident, especially for the nuclear safety, we should recall about how safe is enough for the nuclear systems. So we would like I would like to return back to the basics of the nuclear systems and to discuss about how we should improve the nuclear safety for future development. This is something like a cartoon from my students. As you know, currently the fossil power plant is boiling the water and making steam, generating electricity, and just replacing the coal or natural gas to the nuclear power. It is almost the same system could be used for the turbine. Therefore, the nuclear energy is just replacing the coal or natural gas to the nuclear uranium. And that is the biggest advantage so that we may not have a carbon dioxide. Just a similar system could be used for the balance of plant section. This is one of the biggest advantage for nuclear energy. That is why there are lots of the country is now working on the nuclear systems. So we have a PWR and a BWR. Just recall about a BWR is a phase change inside of the boiling reactors. But the PWR does have a heat exchanger, that is steam generator. This is another system. Maybe currently we have a BWR system is in Estonia. So maybe we may just thinking about that. But this is a very big power plant, similar to the Fukushima Daiichi. So that we may have a natural recirculation pump system, but the BWX300 doesn't have this pump system. Instead of this pump, they have a natural circulation to cooling the fuel to making of steam inside of the reactors. Just comparing with the BWR and the PWR, PWR doesn't have a phase change, but we have a phase change inside of a steam generator. And in this case, this system is completely same as a fossil, coal power plant. So it is very easy to replacing the plant balance of plant side. That is why the many country, including China, is working on the this PWR, or French is also working on the PWR. But Finland and Sweden and Japan, United States, we are having BWR system because BWR system is very simple and the construction cost is not so big because of the small containment vessel systems. But this small containment vessel system becoming the disadvantage for Fukushima Daiichi accident. That is I would like to recall again. Oops. Okay, this is also the cartoon coming from my student lecture. Let's discuss about the difference between the fission and the coal power plant burning the carbon dioxide, making carbon dioxide. This fission, we may generate a large energy, about 200 mega electron volt, just one uranium atom. And comparing with the carbon, graphite, I mean the coal or natural gas may be oxidized to generate the carbon dioxide, which is give us the only 4 electron volt. Electron volt is a unit of the energy. So comparing with this uranium fission and this burning oxidation is big differences. 10 million big difference of the energy sources. That is why we are going for the fission to having a very small amount of the uranium make big generation of the energies, where the carbon dioxide release is too huge with a coal power plant or something like that. But the biggest problem of this uranium fission is generating the many fission products. These fission products are usually the radioactive. And also generating the uranium is capturing the neutron to be the plutonium or americium or curium or another TRU may be generated. And these fission products and this TRU will be the radioactive, very high radioactive sources. So these fission products should be carefully confined and controlled inside of the fuel. Otherwise, we may contaminate the environment by these radioactive fission products. This is the biggest advantage. Biggest advantage is big power source, but the biggest disadvantage is a huge amount of the fission products. So nuclear safety is mainly focusing on this confinement of these fission products. Fission products should be stored inside of the fuel. In that case, everything is okay. This is safe enough. If these fission products could be released to the environment, this is one of the accident. And also the spent fuel is having lots of these fission products. Therefore, we should go for the geological disposal because of the some fission products have a half-life of the couple of million years, or much longer fission products may exist. Therefore, we should carefully confine the spent fuels. So this cartoon just showing the advantage and the disadvantage of the nuclear systems. So we have to carefully taken care about these fission products, which should be carefully confined inside of the fuel, I mean the fuel rod, or inside of the chambers, so that we could safely storing these fission products for a very long time. The time scale of these fission products release control should be around a couple of 100 years to Maybe it depends on the fuel system, but sometimes 10,000 or 1,000 years or something. But anyway, these fission products should be carefully stored for life cycles. This would be the nuclear safety target. Okay, so before discussing about the confinement of this fission products nuclear safety issue, we should recall about what is the safety. So there are lots of the definitions. If I read some textbook, what is safety? Sometimes the safety condition is not a dangerous condition. And I just look at what is the dangerous condition, it's not safety condition, or something like that. So we should, safety and danger is just reverse meanings. But our target, especially for nuclear safety, our target is we should protect human beings. That is the main target of the safeties. So then this human beings protection related to the properties and environment should be also protected. So all of the system, nuclear power station, should be keep safety, and with keeping safety, human beings receive the benefit under these kind of the systems. So to keep safety, we have to control the dangers. Danger is possibility of human life damage. This would be the possibility of properties environmental damage. This is not a usual condition, unusual conditions. So how to get benefit with protecting the dangerous unusual conditions? This is becoming a safety design. So safety design has two target, two concept. First is prevention. That is during the full life cycles, including the preparation. This is the design, construction, and the operation, and the decommissioning, disposal. A whole life cycle, we have to keep the safeties, escape from dangerous conditions. Not only the operation condition, but also the disposal condition, we have to keep it safe. So to keep safe, we have a two strategy, prevention and the mitigations. Prevention is the easiest way. The systems are not broken under normal conditions, construction, operation, disposal. This is a very usual design concept. But although the prevention system should be carefully designed, it could happen the malfunctions. So mitigation is another biggest nuclear safety target. If the systems are broken, the whole system would never be fatal. Fatal condition is a very severe condition. So we are assuming that these prevention systems may malfunction. But in that case, we have to mitigate the event or accident. So this prevention and mitigation combination would be the technique for how to keep the nuclear systems to be safe. So this prevention system plus mitigation system, all system have to be quality assurance of the systems is very important. This quality assurance including the hardware, not only hardware, software, and the human beings, organization, etc. So everything systems have to be assured high quality to achieve prevention system plus mitigation systems. So to do so, as we already know about that, the IAEA proposing the safety standards series. That is, I just copied from the safety standard series. So basic nuclear safety should be identified with the fundamental safety principles, SF1. They may having the fundamental safety concept, and they have general safety principles and specific safety principles. And these kind of the document, they are showing the how to keep the nuclear system to be safe. And we are going for the nuclear power plant. So in this case, SSR2/1 or SSR2/2 will be the some kind of the Bible for nuclear systems. So nuclear system safety should follow this IAEA's safety standards. Just recalling about SF1's fundamental safety objectives is to protect people and the environment from harmful effects of ions and radiation. This is very famous objectives. So we have to keep the people from the radioactive materials. So here, the harmful effects of ionizing radiation is mainly comes from the fission products. Uranium fission products should be protected from the people and the environment from these fission products. That is the most important issue for nuclear safeties. In this SF1, they are proposing the 10 principle, but prevention of the accidents, principle 8, is one of the important issue. This prevention, including the not only prevention but the mitigation, just with using these two strategy, prevention and mitigation, we may keep the people and the environment to be from the fission products. That is the goal of the nuclear safeties. So in this SF1 and following the SSR2/1 nuclear power plant design, they are proposing the well-known defense in depth concept. This is just I may translating with the SSR2/1 to the prevention and the mitigation. And this defense in depth concept, first and third, will the prevention from the normal operation, prevention for the escalating the accident, prevention of the core damage, or prevention of the significant offsite risk. This is first, second, third layer is mainly for the prevention. But this IAEA's defense in depth concept is also combining the prevention to mitigation, mitigate the consequence of the accident, and mitigate the radiological consequence. This fourth and the fifth is mainly focusing on the mitigations. So in the nuclear power plant systems, we may coming for the design operation maintenance is a first layer, anticipated transient accident, maybe the second layer, and the design basis accident. This would be the third layer. So according to the regulation, we should focusing on this design basis accident to prevent the damage or prevent the significant site release. This is be the first criteria for this keeping it the nuclear safeties. And here IAEA is proposing this fifth layer should have an independent effectiveness. This fifth layer, 5 layer, should be independently designed or independently confirmed. But important thing is this fifth layer should have an independent effectiveness. So from the 1 to 3, this is mainly focusing on the design. But after design or beyond the design condition, we have to think about the mitigation of the consequence of accident. This is usually we call it a severe accident management. This severe accident management is now not a design, but an over design condition. Beyond the design condition, we have to carefully check about the severe accident. This is a core melt or severe offset release may happen, but in that case, we have to mitigate the accident. And this is a very important issue for Fukushima Daiichi nuclear power station accident. Because of this concept has been issued in 1990s after the TMI and the Chernobyl accident. But the Japanese government tried to introduce this severe accident management into this regulation. But unfortunately, the Japanese government failed to implement this severe accident management in the regulation, just the voluntary manner to satisfy this severe accident management by the utilities. That is one reason why the Fukushima cannot be prevented. Therefore, after Fukushima accident, this fourth layer, severe accident management, is also taken into account to the Japanese regulation now. And the fifth layer is also the mitigation of the radiological consequences. This is emergency response, evacuation of the people from the accidental site. So this is developed in Japan around 2000 because of some JCO criticality accident happened in the year 1999, and then for after that, Japanese government tried to enhance these emergency responses, but unfortunately this is also not good, and during the Fukushima accident, many people died because of this malfunction of these emergency responses. Because of the evacuation system is not good, so that many people in the hospitalized people cannot be evacuated, or hospitalized people may transferring during the transfer, they may lost their lives. That is why currently we are very focusing on this emergency responses for nuclear safety tools. So as a summary, this 5 layer of defense in this concept, prevention measures should be discussed with a design basis, and also the mitigation, severe accident management. This 4th layer also have to carefully check with during the regulation, and also this should be continuously improved during the operation. So every system may have lots of the operating experiences. That should be considered for the accident management for improving this management capability. I will discuss about later. And emergency response, because of the SMR, the area should be evacuation zone could be small enough. However, still we may carefully design for this mitigation of the radiological consequences. That is, we need to have an independent effectiveness. Okay, so I'll just skip one page, but reactor safety, I'll record the reactor safety again. So this prevention and mitigation, important thing is core damage prevention, or significant offset release should be prevention. So to keep the prevention of the core damage or significant offset release, what we have to carefully check is 3 key safety issues. This is a very famous one. Stop, cool, confine. This is a 3 strategy of the nuclear safeties. Stop means fission chain reaction should be stopped because of the fission chain reaction generate a huge power of energy. Therefore, in case of the emergencies, we have to stop the chain reaction, the fission. To do so, we are having an independent system. One is a controlled scrum, and the other is a boronic water insertion to stop this chain reaction. This is very widely known, and many systems are focusing on this stop. And second is cool the residual heat, decay heat, cooling the systems. Nuclear reactor fuel. Otherwise, the nuclear reactor fuel may be melted. That is to prevention of this core melt. Emergency core cooling system (ECCS) were designed for cooling the residual heat. And the long-term cooling system is also needed for core melt preventions. And the final thing is confine the radioactive materials. So that radioactive materials, that's the fission products. Fission products should be stored inside of the fuel or fuel rod or reactor vessel. Anyway, final barrier is containment vessel. So radioactive materials should keep inside of the containment vessel. This 1 to 3 safety reactors, nuclear reactor safety concept is a very basic of this reactor safeties. So fission chain reaction, maybe I already discussed here. Oops. So fission generating the heat and the many fission products, radioactive fission materials has been generated. And this fission, we have generating a very huge power. Therefore, we have to stop this fission with control rod insertion or boronic acid water insertion. Anyway, fission could be stopped during the accident. That is okay. But another important thing is these fission products are usually radioactive, and these fission products is very unstable, or normally it's very unstable, and the iodine-131 is half-life is 8 days. So this iodine-131, for example, or maybe decayed to the xenon-131, and in this decay, they emit gamma ray. This is very dangerous. And simultaneously, they are having decay heat, tiny heat is generated. We call it decay heat. Because so many fission products are generated, this decay heat could not be negligible in nuclear reactors. So this is some example of the Fukushima Daiichi accident. Fukushima Daiichi accident had been happened in 2011, March 11, and this is 1 year. And this is decay heat ratio to fission. So 1.0 is fission energy generation. But you may know after half a year, 6 months later, 0.1% of the energy decay heat has been generated. This is very huge. For example, the 1 gigawatt of energy has been generated. In this case, after half year, we may still have 1 megawatt of the 1 gigawatt. This is just only 1,000. 1 gigawatt, 1 gigawatt reactor source, 1 megawatt decay heat should be exist just after 6 months. And even 1 year, we still have 0.8%. Or anyway, a huge amount of the energy should be generated by this decay heat. And just after the shutdown, maybe this chain reaction may be terminated, but still we have a huge amount of decay heat. Therefore, we have to cooling this decay heat by water. This is one of the emergency core cooling system, and as I told you, the 1 year, 6 months, 1 year, very long term, we need to cooling the fuel. This is one of the important issue for nuclear reactor safety basics. So stop, cool, confine, these three items, especially for the cooling, the residual heat is a key issue for keeping the nuclear safety. And I will talk about the Fukushima because of the in Fukushima case, Fukushima Daiichi case, we may fail this cooling the residual heat. This may causing the reactor core melt and a big accident. So this is cartoon by the Fukushima Daiichi nuclear power station. We may have a fuel cores here, and the control rod is inserted from the bottom. And this is a reactor vessel. Surrounding the reactor vessel, we have a containment vessel here. And this is a TORA, suppression chamber. And this is a heat exchange system to cooling the decay heat. Actually, after the shutdown, the control rod can shut down the chain reaction. But after decay heat should be removed by these pumps on the heat exchanger systems for long term, 6 months, 1 year, or very long terms. And the Fukushima Daiichi is cooling by the seawater. Therefore, through this heat exchanger system, the core has been long-term cooling system is installed. And stop chain reaction is mainly control rod, and the confinement is fuel rod, reactor vessel, and the containment vessels. This is the key issue for nuclear safeties. I will recall it later. So let's come back to the Fukushima Daiichi nuclear power station power plant accident. This is copied by the Google map, Japanese main island. Here is Tokyo. Tokyo is located here. And in the Pacific Ocean side, we have up to 13 nuclear reactors installed in March 11, 2011. And Higashidori is far away, but this is Onagawa and Fukushima Daiichi, Fukushima Daini, and Tokai Daini. These reactors are installed in this Pacific Ocean. And March 11, 2 o'clock 46, we have a big earthquake happens. This is the epicenter of the earthquake. But this area, we have lots of the aftershocks. So the big earthquakes continuously happen with these locations. And as you may see, the Fukushima Daiichi is a very old reactor, more than 40 years operation. And this is a very youngest, only 6 years operation, Higashidori, or something like that. And I may just show you the scale of the earthquake. Seismic design. This is acceleration. 1.0 is design acceleration is same as the measured acceleration by the earthquake. So Onagawa, Fukushima Daiichi case, because we have a three-dimensional north, south, east, west, and up, down, three-dimensional acceleration is plotted here. So Onagawa, Fukushima Daiichi, almost design acceleration, similar big earthquake has been heated in the nuclear power stations. And Fukushima Daini and the Tokai Daini, about 50%, half of the design earthquake heated. And from this biograph, the seismic design, no damage has been reported, even the Fukushima Daiichi. So we believe that seismic design worked well. And actually, as I show you, the 13 reactors are listed here. And Fukushima Daiichi, into 1 to 3 is a full operation, and the 4, 5, 6 is outage condition. Fukushima Daiichi is all reactors are full power. Tokai Daiichi is all full power. And Onagawa, into 2 is just starting up operation at 2 o'clock. So it is very easily to shut down. And the defense in depth first layer, it automatically shut down. 100% of control strut has been inserted, and it very safely shut down. But Fukushima Daiichi and Tokai Daiichi, they lost the offsite power. But emergency diesel has been operated just after the earthquake. So earthquake has not so big issue. But after 1 hour, tsunami hit the Onagawa, Fukushima Daiichi, and Fukushima Daiichi, Tokai Daiichi. And this is a little bit complicated figure, but the blue line is the design tsunami height. And the yellow part is actual reactor locations. So for example, the Onagawa design tsunami is 9 meters, and Onagawa site is located in the 40 meters from the water level. But Onagawa, the tsunami height is 30 meters, just 1 meter beneath the actual location, and 5 meters bigger than the design tsunami. But fortunately, this is a little bit lower than the actual location. Therefore, Onagawa has almost no damages. And another Fukushima Daiichi and Tokai Daiichi, they may having over the design tsunami. However, they may store location is higher than the actual tsunami. It has not so big issues. But Fukushima Daiichi, their location 1 to 4 is 10 meters, 5 and 6 is 30 meters, and Fukushima Daiichi heated tsunami is 15 meters, and therefore the Fukushima Daiichi has a 5 meter seawater underwater condition, and 5 and 6 is 2 meter underwater conditions. And this is a list of the what happened after tsunami. There is Onagawa and Tokai Daiichi. They have a couple of the DG has been malfunctioned. Emergency diesel generator has been malfunctioned. But fortunately, they can survive because of they have another 2 DG, emergency DGs available. But Fukushima Daiichi and Fukushima Daiichi, they may have a station blackout, and loss of ultimate heat sink may be generated. And Fukushima Daiichi is very dangerous because of the station blackout plus loss of ultimate heat sink could be happened. And Fukushima Daiichi is also station. They have electricity, but loss of ultimate heat sink happens by this 3 unit. But fortunately, they have electricity so that they can survive it. And this unit 5 and 6, this is also electricity is available in the unit 6, and then unit 5 and 6 could be survived. But unfortunately, no electricity and no heat sink. Unit 1 to 3 has a core damage, and 1, 3, 4 got a hydrogen explosion. This is what's happened. So maybe the Fukushima Daiichi is very famous, but I may just recall about Tokai Daiichi because of this is suggests us a very important issue for Tokai Daiichi tsunami protections. Actually, Tokai Daiichi nuclear power plant heated a tsunami. Tsunami height is a 6.3 meter tsunami heated the Tokai Daiichi. And near seaside area, they have pump areas. This is main cooling pump, and this is the emergency cooling pump. 3 units of the emergency cooling pump exist. And year 2010, their tsunami protection wall is 6 meter height. But unfortunately, they decided to increase the wall height to 7 meters. 1 meter increase at 7 meters. So when the tsunami comes, 2011 March, their protection wall is 7 meters. it is higher than the actual tsunami. And therefore, these locations keeping dry. That means emergency pump could be survived. But Japanese fiscal year is end March. Therefore, when the tsunami hit March 11, they are still working, not finishing the some portion. Therefore, this emergency pump has been damaged, and therefore they can survive. These two emergency pump system, two cooling reactor cooling system is available. So Tokai Daini could be survived. So if they are not increasing the tsunami height wall to keep it 6 meters, all of this pump has been flooded. And this means Fukushima, not only Fukushima Daiichi, Tokai Daini may have a cooling malfunction, core damage may happen. This is a good practice for this anti-tsunami protection wall. So they decided to increase the wall height because of the some researchers showing that Jogan tsunami, which has happened 1,000 years ago, may be a little bit higher in this Tokai Daini area. Therefore, they decided to increase the height year 2007 or something. And fortunately, just before the tsunami or earthquake, they increased the protection wall, and they now survived this Tokai Daini. This is important thing is suggesting us is a continuous improvement is very important. So if they think about the new knowledges of the tsunami height maybe a little bit higher than 6 meters, so they increases, they pay big money to increase the protection wall. But fortunately, this improvement could survive the Tokai Daini power station. Now, Fukushima Daiichi. This is very famous. As I already told you, 5 meter flooding happened in the Fukushima Daiichi. 5 meters is very, very huge. Therefore, this water, seawater is leakage inside of the turbine building, reactor building, or something, and the heat shrink may be lost and the station blackout. This is biggest issue. So I may just listed some systems, offset power or offset power has been lost, and the emergency DG, diesel generator, emergency power supply, only one air-cooled power supply has been available, another power supply has been flooded. And another electric transfer system is also some available, but maybe lots of them down. And the DC battery, DC is available only in Unit 3, 5, and 6. And Unit 1, they may have everything lost. This is worst reactor. And Unit 2 and 3, they may also, during the operation, they try to survive. Unit 3 try to survive by DC battery. But after 3-4 days, the cooling system failed. So let's looking at the Fukushima Daiichi. I already told you stop, cool, confine is a 3 key issue of the nuclear safety. Stop is working very well. But because of the electricity has been malfunction, this pump system doesn't operate. So cooling system doesn't works. So cool the decay heat malfunction. This means the reactor core cannot be cooling down. That means core melt happens. And the melted core is passing through this reactor vessel, and the containment vessel also malfunction, and the confining radioactive materials also failed. So important thing is the cool decay heat malfunction is a key issue. Just look at the progression of the Unit 1 again. This is earthquake happens, so they shut down, automatically shut down. And this is an actual chart. this is a reactor pressure, 7 megapascal and 6 megapascal. This is a normal operation condition. And then earthquake happens. This is time progression. And they is closing the confinement valves, separation valves, isolation valves closed. That means the pressure may be fluctuating. And because of the no heat sink exists, then pressure increases a little bit. Then they have isolation condenser systems. Isolation condenser system is steam has been condensed by natural circulation. This is a very simple passive safety system. And using this passive safety system, they may start cooling the fuel. So as you may see, the pressure is decreasing very rapidly because of the cooling capability is very bigger than bigger. Therefore, steam has been condensed, and a reactor could be correctly cooling down. But it's too huge, only 4 megapascal. This is too quick. So that they are closing this passive safety system's valve. And closing the valve, pressure increases. Then open valve, closing valve, open valve, closing valve, they are fluctuating the pressure. This is the operator is working on it. And here we have a tsunami. And tsunami causes a station blackout. Therefore, they can no more operate these valves. So unfortunately, the tsunami hit during these valves are closing. I mean, the passive safety system has been not operating condition. Tsunami hit it. So this is closing condition. The tsunami hit it. So this is certainly the passive safety system. But if they have a valve, if this valve has been not open, this passive safety system doesn't work. So even though we have a passive safety, but it should be operated not manually, not electricity, but automatically operating during the accident condition, passive safety system is very important with looking at Unit 1 systems. So because of this passive safety system doesn't work, because of the tsunami hit it and no electricity, they cannot open these valves. Unfortunately, the system does exist, but they did not operate. And unfortunately, this system doesn't work, so that reactor core maybe the dry outed, and then core melt doesn't happen. So this fails the cooling the residual heat systems. Okay, doesn't work. So after that, they are trying to supply the water from the fire engine, and then it is now the normal operation condition, but they may be falling down, and unfortunately, they may have a hydrogen explosion also happens. And into 2 and 3, it has a different systems. They do not have an isolation condenser system, but RCRC is a steam turbine system to supply the water. This operated into 2 and 3 for a couple of days. And unfortunately, after a couple of days, this system doesn't work because of the DC control electricity has been lost. This is some kind of the passive safety system, but long-term operation is not available. Into 4 is not operating, but they are doing the outage. Lots of the fuel has been stored in the spent fuel pool. Spent fuel pool. This is 3 months ago. They are stopping the reactor. Therefore, this spent fuel pool has still a huge amount of the power, and because of the no electricity, this water level becoming decreases with the boring. And fortunately, we may have a concrete supply system to supply the water, 1 week later, and then finally this spent fuel has not been melted. But this Unit 4 event reveals that spent fuel has been melted. In that case, this is no confinement. If spent fuel melt happens, this radioactive materials inside the spent fuel is directly released to the atmosphere. Therefore, after this Fukushima event, spent fuel pool cooling ability is strongly improved, especially in the IAEA suggestion. All of the nuclear power stations around the world, spent fuel pool cooling ability is improved. This is the lesson learned from the Unit 4. Anyway, cooling is key. Unit 1, 2, 3, 4. All system cooling fails, and this is cooling successful. But another 1, 2, 3 cooling fails. This is important issues. So from this lessons learned, continuous improvement. As I already told you, Tokai Daini nuclear power station. If we have a new knowledge, we should improve continuously. This is a very important issue. That is lesson learned. And the passive safety system, we have passive safety system, especially for the passive cooling system. All 4 units, cooling is a biggest issue. But the passive feature should be checked with the system's viewpoint. If the passive cooling system doesn't start passively, it may not work during the accident. That is the biggest lesson learned after Fukushima. So learning from this Fukushima event, we may now focusing on the accident management. This is IAEA's defense in depth concept, 4th layer. We have to mitigate, even though the core melt happens, we should mitigate the accident. Accident management should be very important to taking care. And after Fukushima, Japanese regulation is mainly focusing on this accident management improvement. And also the common cause failure consideration. This time we have electric power is caused by the common cause failure. But another is also cooling water, may also the cause of the common cause, and the human beings. This is related to the safeguard or security. Also have a common cause, so we should carefully think about common causes. Anyway, now I'd like to discuss about this accident management a little bit. So I already told you the defense in depth concept. These 4 layers mitigate the consequence of the accident. This issue is one of the important issues. So IAEA's accident management guideline, SSG 54, is defined accident management as a taking of the set of actions during the evolution of an accident. So this is showing the 2 concepts: to prevention of the escalation to a severe accident, to mitigate the consequence of the severe accident. So prevention and the mitigation combination is suggested by the IAEA's guide. And then achieve a long-term safe, stable state. This is because of the, as I already told you, the residual heat is very high enough, even though the 1 year later, this means a long-term safe state is important. So just after the accident, prevention, the mitigation is important, but for a long term, we should keep it safely. So think about the accident management. Yeah, I may also show you some lessons learned from the Fukushima Daiichi event. As I already told you, the Fukushima Daiichi nuclear power station, we have Unit 1, 2, 3. Containment vessel design pressure is 2 bar, but actually its pressure is increasing to 7 or 6 bar, double or triple of the design pressure. And to prevent the overpressure rupture, they try to going for a venting system, release steam to the atmosphere. But Unit 1 successful, it's 3 successful, but Unit 2 doesn't work. And but in 1 and 3, venting does works, but a hydrogen explosion happens. And in the 2, venting doesn't work, and quantum vessel rupture happens. It may be a little bit 1 day or a couple of days later. So important thing is if core melt happens, if all of the 3 need core melt happens, we have to prevention of the quantum vessel rupture to preventing radioactive material release. This is one of the important issue for accident management. So in Japan, we have not installing this kind of system, but looking at worldwide, Finland and Sweden and Switzerland, European country is introducing a filter containment vessel venting system in year 1990s. And also the over temperature rupture, they have also a heat removal system, additional heat removal system. But today I'd like to discuss about this filtered containment venting systems that has been installed BWR system in Switzerland and Finland and Sweden. Unfortunately, we do not have it. So I may show you the Unit 1, Fukushima Unit 1 overpressure histories. So this is a reactor vessel cartoon, and this is 6 bar, very huge pressure. Therefore, they try to release the steam to atmosphere. They try to open these valves, two valves. But unfortunately, this valve could be opened, but this valve cannot be opened because of the high radiation, very high radiation of this area. Operator cannot come to these valves. So they try to open this, because this is air operating valves, so they try to open this air operating valves, and fortunately, they open these valves, and finally, they release the high pressure steam into the atmosphere. Oops. This is the actual photographs I found. This is released to the atmosphere. This is highly contaminated steam could be released. That is what happened actually. And looking at the filtered venting system, Leibstadt nuclear power station. This is BWR, Switzerland BWR system. And Switzerland government ordered the mitigation of the severe accident. They ordered backfitted in 1992. They are installing this filtered venting system. In case of the high pressure of this contaminated vessel, it automatically release the steam to the atmosphere. And also they have a filter so that cesium, strontium may be captured inside of this filter. And filtered steam could be released to the atmosphere. This system has been implemented year 1992, more than 30 years ago. So Switzerland has this system. But unfortunately, Fukushima doesn't have these systems. So in 1990s, we are discussing about the installing the filtered venting system in Japanese reactor system. That is more than 30 years ago. We have a discussion. So emergency venting system. So overpressure rupture prevention. We need to have a venting system. So in Fukushima, they are installing this hardening venting systems. And the filtering activity is passing through this huge amount of the water in the suppression chamber, releasing through this suppression chamber. Many radioactive materials has been captured in this water, and filtered steam could be released. This is what we thought 30 years ago, Japanese system thought. But comparing with this Switzerland system, there, if pressure increases, they automatically open these systems. And also, filtered venting system is separately installed. So both two systems have the same function. But a viewpoint of the system is the viewpoint. This means a station blackout or any kinds of the accident consideration, very different systems. So, filtered venting system, Europe, independent venting line, no plate without power supply, they can operate. But the Japanese system, power supply was needed to operate. Difference is very huge comparing with this Fukushima and Japan and the EU system. Although Japan has an earthquake, but nowadays all of the nuclear power stations in Japanese BWR are installing this filtered venting system. It's too late. If the Fukushima having this filtered venting system, not so many area, evacuation area could be small enough. Unfortunately, the Japanese government decision is not, that time's decision is not good comparing with the European government decision. So we should think about the comprehensive system viewpoint should be important. In case of the severe accident, no electricity case, it can be operable or not operable. This is big differences. Okay. It's my last slide. So comprehensive risk reduction is important. Severe accident management, core damage prevention, mitigation, and long-term stability. And we need to have a nuclear management for safety. Passive safety, even though the passive safety system, we need some kind of management. Okay, thank you very much. That's all for my talk.
Is there any questions? Oh.
Hello. Thank you. My name is Kalev Kallemets. A technical question. In 2019, I was shown in Canada passive hydrogen combiners.
Mm-hmm.
And as we know, we had a hydrogen detonation in several units. Has this kind of passive hydrogen combiners that are just boxes like you have it there, that are combining hydrogen to avoid hydrogen kind of a saturation in the atmosphere there?
Sure. Actually, in BWR system, they may have active, not passive, active hydrogen combiner is installed. They need electricity anyway, but they are installed it. And another thing is they are inerted environment. I mean, inside of the containment vessel, nitrogen inerted environment. Therefore, during the operation, no hydrogen explosion may be considered. But unfortunately, in Fukushima, this hydrogen had leaked into the reactor building. So reactor building had a hydrogen explosion. So now current Japanese regulation system is ordered to installing the passive hydrogen combiner inside of the reactor building, not the containment vessel. And the PWR system, we also, lots of the PWR system in Japan, they are installing the lots of the passive hydrogen combiner inside the containment vessel in PWR. PWR containment vessel is not inerted. That is why the hydrogen combiner has been installed. Actually, after the consideration of the hydrogen explosion in the TMI, the Japanese government tried to install the hydrogen recombiner, but it was that time active recombiner. now it's passive. So should be passive safety. Passive is very important. After TMI, we are thinking about that, but the consideration, passive consideration, is not enough. Now it's improved.
Yeah, I have a question regarding, has there been many changes to the regulations, and has these caused, let's say, difficulties for the operators, and
Sure.
How big impact?
Very big impact, very big impact. For example, the filter venting system, Japan has a huge earthquake, earthquake country. Therefore, the filter venting system has been stored inside underground. Very big hole is digged and the filter venting system has been installed underground because of the seismic protection. And that means pipeline becomes very, very long to supplying the filter venting system. This may cause the another issue of the accident management problem during the accident because of the such pipeline system becomes very high radiation. So this is very big issue. And many Japanese nuclear power stations, in especially BWR, has paying big amount of the money to upgrading the safety system, including the passive safety and so on. And also the Japanese government regulation ordered the airplane attack protection. To do so, they may order the secondary cooling system. Additional secondary independent cooling system has been ordered. Therefore, it may cost almost constructing the new reactor. But Japanese utility pay big money to preparing a restarting. So currently the 12 unit has been restarting, all PWR. Another couple of reactors are waiting for restarting. Shimane, Kashiwazaki, Karia, Onagawa, they are BWR. BWR will be operating maybe the end of this year. First Onagawa, then Shimane, and then Kashiwazaki, Karia may be operated not so long time. But I expect it for BWR will be restarting this year or next year. Very big problems for Japanese utilities.
Thank you for the great presentation. I'm from the regulatory side here in Estonia, so I have two questions.
Mm-hmm.
I don't know the first one, is it your area or not, but you showed in the first slide what is the benefit of nuclear. So we have a lot of energy, and what's the downside? The biggest downside, we have the very active fission production. And can you give us a couple of words, what is done in the nuclear world to tackle the downside? Because there are, to tackle the downside, yeah, to deal with those fission projects, to make it more beneficial.
Sure.
So that the people get some kind of understanding that this is not only a downside anymore.
Yeah, that is a recycling process. So that we are recycling the spent fuel to extract the plutonium and the uranium-235 to making the another fuel. Extracted plutonium could be used fuel, nuclear fuel. That is MOX, we call it mixed oxide, MOX fuel. And simultaneously, the radioactive materials has been concentrated. So volume of the high radioactive waste will be reduced very big amount. Therefore, if the Japan has a lot of the spent fuel. Spent fuel is a very huge amount of the area is needed. But if we are reprocessing and make a very strong high-level radioactive waste, maybe it is stored inside of this room. Very small amount. So this is a big advantage. That is why Japanese government is trying to go for reprocessing to reduce the high radioactive waste, and we can reuse the plutonium as a fuel. That is Japanese governmental issue. Maybe the Japanese governmental, he also showing this.
Thank you for that. I wanted to hear. And the other question was just, I'm pretty curious, you showed a slide where the different MPPs were designed to design basis events. Different one is for the tsunami. And although we usually take the very conservative approach to us, assessing the designs, in this slide was shown that in any kind of MPP in Japan, the design basis was much, much lower than the actual tsunami.
Sure. That is big problem. That was big problem. For we have a lots of the earthquake, Kobe earthquake or something, big earthquake. Therefore, we are always think about preventing the earthquake. So we are sharing the very conservative assumption. So very huge earthquake, we can protect it. That is our strategy. But we are also think about a tsunami. But unfortunately, more than 1,000 years, we do not have such a big tsunami. Year 2004, we have a tsunami in Indonesia. That Indonesian tsunami is very huge. But if we may think about seriously about the Indonesian tsunami, we can rethink about the tsunami protection. But unfortunately, that time, nobody think Indonesian tsunami will never come to Japan. That is a big problem. What was a big problem? But unfortunately, the similar tsunami hit in Japan because the Pacific Ocean is connected. So fortunately, this area, Baltic area, Baltic Sea doesn't have such kind of the big earthquake or tsunami, but maybe some kind of the melting of the Arctic ice or something. So I'm not sure, but think about some external event should also be carefully considered. So we know the fear of tsunami, but we are underestimating the tsunami that time. That is a big problem for us. Now we are assuming a very huge tsunami. Thank you.
Okay. Thank you.
Thank you very much.